actions, some of them are ductile. We call them deformation control actions. And some are brittle, we call them force control actions. So know that from point of view of a engineer in charge of evaluation, when we look at a building, we see lots of deformation control action, lots of force control action. If we look at another building, we see lots of deformation control action, lots of force control action. So as this status of these deformation control actions and force control actions, in each element, in each type of system, what is the ductile and deformation control action, which one is the brittle one, force control action, the code for the existing building identify that. The different chapters on different systems says that, for example, if your system is a moment resisting frame, in this beam, the bending moment is a deformation control. And all other actions are force. So we deformation control is axial load, is force control. This shear here in this beam is the force control. This torsion is force control. So now that we look at the building from the evaluation point of view, and the building is divided to some deformation control actions, some force control actions. Now, what is our job? To look at the demand and capacity for them, and check for each action, either force control or deformation control, if their capacity is more than the demand. So our whole story is how to calculate capacity and demand for each force control or deformation control. In our 2 days talk, this approach is much simpler, because our 2 days talk is about the nonlinear analysis, and behavior of the building in earthquake is nonlinear. We ourselves accept the damage buildings during earthquake, otherwise it's not economical to design buildings for the earthquake. So the behavior is nonlinear. Today we want to talk about nonlinear modeling, so these two are very compatible. But in the previous session on linear analysis, we have difficulty to calculate demands for the force control and deformation control, because we want to somehow mimic the nonlinear behavior through a linear analysis. So we should do some adjustment, because linear is linear, nonlinear is nonlinear, and when you use a linear tool, you can't expect that you can get a realistic demand distribution in a nonlinear system. Therefore, we should do some adjustment. Therefore, our job in the previous session was much more difficult, because we look at the building that we want to evaluate. We saw lots of deformation control parameters, lots of force control parameters or actions. Then we want to apply loads, and then apply load combinations to estimate the demands. But because it's linear and the behavior is nonlinear, we were using different load combination, the force control actions, and different combination for different control actions. So it was a little more complex. Here tonight we use the same because the modeling and analysis can take care of the distribution of damages. So there is no need for us to ourselves adjust the things that our tool, which is linear, cannot handle. So in that story, as mentioned, one part is calculation of demands, and the other part in the previous session on linear analysis was the calculation of the capacities, assuming that now we have the demands for that beam, we have the demand, we have the bending moment on this beam, and also we have the shear in this beam. One, deformation control, one, for example, force. So what we do with that, then we have the demand, and demand means the value of that in load combinations. Now we have on with the capacity for those control actions, capacity is simple. For force control, for scary ones, for brittle ones. For them, then we just look at their strength. We don't want to check their plastic, for example, behavior, because we don't want them to go through that range of behavior. If they pass the strength limit, then they are gone. Therefore, it's easy for the force. Every one of the actions that are categorized as a force control action, we just need to know the capacity of that, strength of that, and among the capacities, their strength capacities, the force bearing capacity of that, and compare with the demand. But how we calculate the capacity? Whatever formula we have for example, calculation of shear capacity of this beam. We want to check a force control action, which is shear. We have the demand. Now we want the capacity. Whatever formula in different code for example, in BMBC is offered to calculate the capacity, shear capacity of the beam section, we use that. But the only point is when we want to put the material characteristic in that formula, we will use lower bound material. So from the systematic evaluation point of view, each material, each different element of the building has two numbers, two values, two strengths. One is the expected, the average, if you do test, the average value, and one lower bound, average minus one standard deviation. So the material is the same, but the value that we use for the force control actions, for the scary ones, we use a smaller value for the strength of it. So it's the general approach is not that difficult. Now, for when we want to calculate the capacity for the force control actions, there is nothing new in the code for existing. All the formula for capacity calculation are the same. Just the value of f prime c or fy that we want to put in the formulas will be lower. B minus 1 standard. So that's then what remains from our video is the set of parameters. These are friendly parameters, the ones that if they get damaged is not a big deal. but we want to measure their damage. So in the previous session on linear methods, because we couldn't get the plastic deformation of the elements because it's linear analysis doesn't give us the plastic deformation, doesn't give us the ductility, doesn't give us the nonlinear damage. We look at the data. So for the capacity, when we want to compare the demand, we define different performance level, IO, for example, immediate occupancy, LS, life safety, CP, collapse oriented, and for each of them, we accept some level of damage. And what that means, for each of them, we accept a level of increase with respect to the capacity. And this is defined by M values, which is equivalent to R value, but is element based. So for each element, for this beam, that we were discussing about, this beam, and this bending deformation control parameter. Now we want to know the capacity there in the tables for each beam. The conditions, as we will see later, based on the condition, gives us M value for I value, M value for CP, or it means the amount of damage that is acceptable in these deformation control parameters at O, LS, or CP level. M, if it's M for IO is 5, it means that in this deformation control parameter, in this bending moment, the moment of capacity, it is satisfies the IO performance level. The same for the LS or CP. So we have M factors there that shows different level of acceptable capacity. And the different level of capacity performance that you accept, different on the level of damage that you accept. Performance level is damage, the level of accepted damage. So our story there finishes this way, that in the elastic, in the linear approach, we have M values for deformation control actions. The only thing that I should remind is that for the deformation control actions, again, when we want to calculate the capacity, again, the same formula as new building codes are used. Just the value of material properties, characteristics, such as F prime C or Fy, will be expected because they are not scary parameters. So, in the previous session, we did a review of those. Also, we mentioned that the main limitation that based on that we select linear or nonlinear is mainly the irregularities in strength. And then the main point that we select static or dynamic for each of them, nonlinear static or nonlinear dynamic, linear static or linear dynamic, is depend on the irregularities in strength, in stiffness and mass. So mass and stiffness irregularity, if exists, is better to do that. If not lots of mass or stiffness irregularity exists, it's better to go. We can go with the static. If there is lots of irregularity in strength, it's better to do. But tonight we want to discuss about the non approach and the approach that from beginning the codes for existing buildings prefer, which is static. And so static nonlinear is the main, the governing analytical method in the codes for existing buildings, is by far pushover. Okay, so what we expect from tonight to review the steps for the nonlinear. There is not much limitation for using nonlinear analysis method. Just if the higher mode effects are important, it's better to use dynamic, not static. And there are, in different codes, there are checkings that we can apply to see if the higher modes are important or not. For example, they say you do a response spectrum analysis on your building and calculate the story shears. When you are doing the response spectrum analysis, you use just one mode. Tell the software just use one. And then use more modes. As usual, number of modes that effective mass be more than 90. And then if any story, the difference between these two, the results of the story shear in any story is more than 30%, shows that higher modes are. Something like that. So there are some criteria that they recommend it's better to use. Other than that, there is no big limitation for the nonlinear methods. There are preferable methods in the existing buildings. Then tonight we will talk about the modeling of deformation control parameters for nonlinear analysis, or one of the most important, one of the most exciting innovation in the existing codes, and one of the very important contributions of the existing building codes is this number: modeling of deformation control.
Sir, if I may
Modeling
interrupt
of force
you,
sure, of course.
many
Please.
people are saying that the voice is a little low. So if, sir, if you could kindly speak a little up or bring your microphone closer when you're speaking.
And please, Salam, again, inform me if that happened. And it's good that our colleagues are giving feedback. So
Yes.
now I try to louder.
Yes.
Okay. So for the number 4, modeling of force control parameters, there is no big deal. Force control parameters, force control were those actions that we don't want to get nonlinear. So their modeling is linear. It's the same as we do in our ordinary design. So there is no big issue in number 4. Number 5, is a formula that instead of calculation of the base shear here in the nonlinear static approach, we should calculate target displacement. So base shear was the quantification of earthquake in elastic analysis. Target displacement is quantification of earthquake in nonlinear. When they call check at this level of earthquake, it give us a target is 5 centimeter target displacement. They say check it for the bigger earthquake, it gives, for example, 7 centimeter. So that formula, and number 6, the same as number 3, is one of the main contribution of these new approaches in the codes for the evaluation of existing building, the acceptance criteria. So nice, so beautiful things that we will go to, hopefully. Regarding the steps, in the analysis, nonlinear analysis, we will have to provide some inputs to our software. So we need a software that can do nonlinear analysis, that can change the stiffness matrix for the elements that get damaged. Now that, for example, we have the software, before we didn't have, but when this kind of analysis, before this kind of analysis was limited to research. So many of the softwares that are for professional analysis, they didn't have modules for nonlinear. But as soon as they doing nonlinear analysis come to the professional work, professional engineering work, they put immediately the modules for the nonlinear analysis. So now they can do the step-by-step, for example, nonlinear analysis. What they ask from us to provide to do their job, one is the target displacement. What is target displacement? They need from us that we make estimation of the maximum displacement of this building in the earth. As I mentioned, one of the most fundamental question in earthquake engineering. If we have a building and if we have the level of earthquake, what is the estimation of maximum displacement of the building? We call it target displacement. So naturally is a point of demand, because everything that is related to loading is demand, and and demand is not unique, is depending on the load. For large earthquakes, target displacement, for smaller earthquakes, the target displacement will be small. Therefore, target displacement is one of the most important inputs in the pushover analysis. But this target displacement will be at a specific form, which we call it control point. And the control point usually is the mass center of the roof. So we expect that during pushover analysis, our software will push the building till the center of mass in the roof reaches to the target displacement. And that's the scenario. That's the idea. That when you push the building nonlinearly to the target displacement, then you have the status of the building in the earthquake, the maximum status of the earthquake. So look at the elements, wherever is damaged is a good estimation of the real damage. Look at the forces, is a good estimation of the forces. Deformations, So when you push a building non-linearly to target displacement, then you can evaluate your acceptance criteria for whatever engineering demand parameter that is considered by your code. If a code asks to check the drifts, we'll check the drifts. For the performance-based codes, we may usually check for the evaluation of existing building, we check the plastic deformation of the elements, deformation control actions. So the story will have three endings. Either you push the building and this building can't reach to the target displacement. Either because the software needs it becomes numerically unstable, so we try to solve the numerical stability. It's not a physical instability. The equations, solving the equation becomes very difficult for the software as you deform that building to the nonlinear range, because little by little the stiffness matrix, the elements on the main diagonal of the stiffness matrix become smaller, so inversing them becomes very difficult for most of the algorithms. So it's numerical. We try changing different software usually tries to do its best and reaches to targets. But sometimes it's not a numerical problem. You ask for this building, the demand in this level of earthquake is, for example, 50 centimeters, but the capacity of the building is 5 centimeters. So whatever you push it, it doesn't go more than 5 centimeters. That's one result, possible result. So then what happens? We say the building will collapse in that earthquake. They ask, what performance level your building achieved? We say nothing, it collapsed in that area. So if you want that, for example, life safety, collapse prevention, immediate occupancy, operational behavior from this building, you should retrofit. The other outcome is that when we push this building to reach us to target displacement, one of the force control actions passes the strength limit, which is at the bottom. These two are the force control. For example, axial load and shear is. So as we push, if the axial load increases, passes this, and this point on the vertical axis is strength, and when we calculate the strength, we use the lower bound values for the material, so it's the lower bound strength. If passes, again, the building collapses. Any of the force control actions, if passes the limit, the building is the second possible ending for the pushover. The third one is that when you push it, as you push, these force control actions, they come, but doesn't pass the limits. But the deformation control, like as here bending moment versus bending deformation, if this passes, because it's a ductile behavior, has some level of ductility. So if this passes the yielding point and the stiffness becomes almost zero, becomes the mechanism, We measure, we expect the software measure for us the amount of damage of this plastic deformation, this ductility demand. The ductility capacity of this is this capacity. But the ductility demand of this is so. Uh, in the third possible ending, the force control parameters won't get damaged. The building reaches target displacement, but some of the deformation control parameters will pass their limit, get damaged, and we assign the performance level of the building based on their damages, as we will explain later. So the software needs a load pattern by us that we tell the software that when you are pushing this building and this point wants to reaches to target displacement, step by step use this pattern. The ratio between these forces remain constant during. The values increases, but the ratio, the pattern remain constant. And naturally, if you push a building to the same target displacement, but with different load distribution, you get different results. With one load distribution, you get damages here. With another load distribution, you get damages here. In one, another damage, load distribution. So load distribution is very effective in the damage distribution and response distribution. So the code should define as an input what load patterns we should give. We expect from our existing code to tell us this and the modeling parameters. Before for research, we for a long time in the history of research, the people, the researchers were doing the nonlinear process. But for having these modeling parameters, they had to do full-scale testing of the elements to get for elements the behavior of the modeling parameters. And because when you to study the nonlinear behavior is dependent on the size. It's not like, unfortunately, it's not like a elastic linear analysis. That, for example, even for a study of wind, we make a smaller model of the building in the wind tunnel, and then we extend the results to the real building. For the nonlinear behavior, it is very difficult to extend the results from the smaller model to the bigger ones. So they had to do full-scale testing to get. Because of that, we much appreciate, as a structural engineer, we much appreciate the modeling parameters that is provided in these building codes. Very strong point, very effective, very powerful advocacy. So in short, there are 4 main inputs for the push-up analysis. And later we will focus on the how to calculate the target displacement. Control point is known. Load pattern is given by the code. And the modeling parameters also depend on the properties of the element, what is given by the the general approach will be by using those inputs. Now we have for force control actions. We have, as I mentioned, very easy modeling, the same as our ordinary. And for element, the section area is given, the stiffness and the material properties, the E is the, even you have the stiffness. Software has the stiffness. So there is no new thing for the force control action, except that when we calculate the strength, the formula we put the lower bound value for the material properties. Other than the problem. And for this deformation control, again, this part is given by the code for existing buildings. So we model the building in the software that is capable to do the nonlinear analysis. Either software already has these requirements building inside, or we give the property to the of elements to the software. Software is ready. Building is modeled. We say push it with this load distribution, for example, with the triangular load distribution, with uniform load distribution, with whatever our code asks, and push it till the top displacement reaches to this target displacement. For example, here, this is 0, 0. We say that push it to, for example, 20 something. But it seems that it can pass the 16 centimeters. So we say that this building doesn't withstand that level of earth. We say, okay, let's try another earthquake. So this building, it seems, can't withstand, for example, the earthquake with 2% possibility in 50 years. Try it with 10% in 50 years. Ordinary design level earthquake. So, for example, for that, this building is around 13 centimeters. So the software begins to push the building, pushes the building. Everything is elastic. All of these elements, their actions, when we look at this building, we see just force control and deformation control actions. As we push, they are increasing, their demand increases, they have one capacity or the many different demands based on the level of applied loads. So the demand increases, then here some of the deformation control parameters, they pass their limit, become damaged, but they didn't pass the capacity of the damage capacity that they have. They didn't pass the ductility capacity. They didn't pass the plastic deformation capacity of there. So, but the stiffness of this element is not this much anymore, 0. So the contribution of the stiffness of this element to the building stiffness gone. So the building stiffness reduces. And little by little, the building stiffness reduces because much more deformation control elements get damaged till it comes to this point. And then software can also give us some, this one. This. So even they give us the tables such as these, that each step by step, at the first just the gravity load was applied, then step by step that the lateral load is increasing. What happens to this building? And those deformation controlled parameters, those plastic hinges, those places, fuses, those places that can get damaged, and the damage, getting damage is not forbidden, but the level of damage is important for us to measure as a performance level. They both can be shown graphically, or here shows that at each stage, each step, how much is the top displacement, how much is the total shear that applied with that load pattern to the building. Also, in this building, this many plastic hinges, possible force control, deformation control parameters we have, this many. All of them are between A to B. All of them are between these 2 points in the elastic range. But as the steps increases, as the buildings pushes more to the inelastic range, we can see that now we pass from the B to we have some between B to I. B, for example, here is I. We will see later. So some of them is here. Some passes IO. This many, for example, at this stage are between IO to LS. And at this stage, for example, 29 of these deformation control parameters are between life safety to collapse prevention. So very nice information is provided. These softwares now is so easy that people that don't want to do evaluation, they do their ordinary design. But because the capability is there, says, okay, now let's see, let's try to see what I designed, what is the behavior of what I designed. So they push their building in the software and see that the building that they designed, why so sharp changes the nonlinear range, maybe it's better distribute the strength better because it's, for example, it's so sharp passes to the, or is why I have this many hinges, damages in the columns. So maybe I better do that. So give us a good sense about our even ordinary design. These software capabilities now are a strong point. Okay, so that will be the general approach. Now, what we need to start our journey for nonlinear pushover analysis, again, we will start from the performance objective. Usually, they ask for a checking of performance objective for us. As mentioned, codes for the existing buildings has the capability that whatever level of the input from the earthquake hazard can be applied. We had discussion that in a session, previous session, that maybe we don't have the characteristic, the response spectrum of the earthquake. We will talk about that. Okay. But in general, as a starting point, they say that check this performance object. That whether this existing building can attain this performance level under this level of earthquake. If you remember, when we were talking about the comparison between base shear formula for existing buildings and base shear formula in the BMBC, we said that there is a very obvious difference. There is no R factor in the existing building because the R factor, real R factor for existing building will be very small. So we forget about a factor for R. We go and for everybody, for every element, find their M factor. But there are also another factor is missing in the base shear formula for existing buildings. And that's importance factor, structural importance factor. In the BMBC base shear, there is an importance factor. But here in the elastic analysis, linear analysis, we didn't have importance factor. Where is importance factor? Are you be treating the hospitals with schools with the ordinary structures the same? No, in performance-based design, you don't need a importance factor, a prescriptive importance factor. For example, if your building is important, you can say, I want life safety instead of this level of earthquake under this level of earthquake. So explicitly, you can select what you want from this building instead of implicitly by a factor you try to reach to a performance level and for example using 1.5 1.4 but there is no guarantee that if you increase the design base shear by 1.5 you get better performance. Sometimes your performance get worse, usually get better, but you don't have a sense in general. But here you select the level of earthquake and level of performance as if the building is important for you. You want better performance under larger earthquake. You select that, and then you will go and check it. Explicitly, you check the level of damage that is under that earthquake will be the building. So you check, not just increase the, for example, importance factor, increase the base shear, and you hope that it gets the behavior of the building instead of life safety. It goes to the, for example, immediate. We hope. We don't check. But here, we check. So there is no need to even I factor, the importance factor. Therefore, we then have a very short definition of the parameters to check. So there is acceptance criteria, quantifiable. But for example, for life safety, it says, what is life safety again? When we say that this after earthquake, if you go and visit a building, if this is there, we say that it performs life safety. Some residual strength and stiffness left in all studies. Some residual. Gravity load bearing elements function. So fortunately, it not collapsed. No out of plane failure of walls. Some permanent drift. Very interesting. So building is not anymore straight. Yes, it has some permanent damage. Damage to partition. Continued occupancy might not be likely before enough repair. So you can't stay, even satisfy the life safety, but the life safety means this. Building might not be economical to repair, which is true. So most of the buildings that we design provide the life safety, but after earthquake, they are not, should be demolished. These are what we see in the structural element. For non-structural elements, as falling hazards, such as parapets, mitigated. We don't have this kind because it's life safety. So when we say life safety, they shouldn't fall. But many architectural, mechanical, and electrical systems are damaged. Many architectural, mechanical, and electrical systems are damaged. We call this life safety. So most probably we can't repair the building. And if we compare with the new building code, it says the life safety for in the existing building code is somewhat more damage and a slightly higher life safety risk. So these descriptions is what, based on that, those limits that later we see in tables are quantified to give these qualities. So we start with this, then the most important formula that we have, or most probably the only for, no, there are a couple load combinations and things that we will see later, but the main formula that we have for tonight is the target distance. Seems a little more complicated than base shear. Base shear was very nice, just SA and a couple coefficients to just adjust for some events. But here is we have some strange stuff here too. But other than that, there is SA at the previous one is A times G, because usually it's SA is a factor of G. So to make it meter divided by square second is to multiply by G. Then we have three factors that we should discuss a little bit about them. So you have a equivalent period of the building. So we should also discuss about that. So these things, we should talk about these things. What is the each of them? Quickly for now, look at the long description of them, but later we will focus on each. So C0 is modification factor to relate a spectral displacement of an equivalent single degree of freedom system to the roof displacement of the building multiple degree of freedom system. Very long definition. So in short, when we from the spectrum, response spectrum, which is for single degree of system, when from there we get the displacement, what will be the displacement at top of the building from a relation between that and the building. This what is C0. Okay, C1. Remember, if there is because this spectrum comes from linear behavior. So for nonlinear behavior, how much displacement changes if building behaves linear or nonlinear is C1. If the details are not good, C2. So C1 is modification factor to relate expected maximum inelastic displacement to displacement calculated for linear elastic response, and C2 modification factor to represent the effect of pinched hysteresis shape, cyclic stiffness degradation, and hysteresis duration of maximum displacement. So all the deficiency in the effect of deficiency in detail. So look at them one by one and more. First, SA, response spectrum acceleration. The effect of earth. So it's an input for us. It's not an important issue for us to calculate. They should provide us. Or they say you yourself go and calculate that based on the site-specific hazard analysis. Or use just the BMBC curves, response spectrum curves for the this level of earthquake, Gizon level earthquake, it is good enough. So anyway, if 10% in 50 years return period, 475 years is selected, it is really just to use the MBCC, but sometimes it's worth to do site-specific, because for this site-specific, maybe you get a smaller value. It's a specific site, and it becomes even your retrofitting becomes even cheaper. So many times it's better to do site-specific responses. Anyhow, one very important aspect is we should have this curve. For example, one of them based on the soil, this curve for the given level of Earth. So we have this now. So what we can get from this, if we have the period of the building, it gives us the maximum acceleration. So if you have the period of the building, it gives us the maximum acceleration. For the base shear in linear analysis, giving acceleration was good, because acceleration times mass becomes force, second law of Newton. But here we want displacement. We don't want force. So this acceleration is not that interesting for us, but what we have usually is the response spectrum. If you have the period of the building, you get the acceleration, maximum acceleration. Is there any way that I get a good estimation of the, is there any way that we get a good estimation of the displacement? Yes, of course. Just as estimation is not accurate, but just as estimation, if you have the period of the building, calculate the omega of the building. Is usually 2 times pi divided by t. So you get the omega. Then if you have the omega, if you divide the acceleration by omega squared, it gives you a good estimation of the displacement. If divide by omega, you get a good estimation of velocity. What are these that I'm saying? These are not very strange stuff as you. Is this, that for harmonic motion, when something is under harmonic motion, sine or cosine, or some of them in harmonic motion, if it moves in a harmonic motion, so for example, the deformation is A times sine omega t, what is the maximum displacement? Sine, it is 1 and minus 1, maximum is 1, so A is the maximum. So maximum displacement, we want this, we want maximum displacement. Maximum displacement is A. What if it, the motion was harmonic? But earthquake motion is not harmonic, but for a good estimation, as an estimation, we assume this one. Then velocity is derivation of the displacement. So if we do that, it becomes sine omega t becomes omega A cosine omega t. And maximum of cosine is 1. So omega times A, omega, what is omega? 2 pi t. It depends on the period of the building. So just check what is the T of the building, 2 pi times that, and then multiply that by A. If you have the displacement. This way you can get the velocity, maximum velocity. And of course, another derivation, then it becomes squared omega times a, and so absolute value, the sign is not important. So the maximum acceleration is omega square a, velocity is omega a, displacement is a. So for harmonic motion, there is a very nice relation between maximum acceleration, maximum velocity, maximum displacement. So interesting. So if you have the response spectrum curve, you easily can calculate the maximum acceleration of this building. But if you want the displacement, divide it by omega squared. If you have the maximum velocity divided by omega gives you maximum displacement. Multiply by omega give you maximum acceleration. So nice, so easy. So here this SA is divided by omega 2, omega squared, omega 2 pi divided by t here under this. It was omega. So this is omega squared. So it's nothing. It is a little, seems a little complicated, but it's not. It's just you had the acceleration. You had the acceleration. You divided the acceleration by omega squared. And omega squared is 2 pi t, or squared 4 pi squared t squared. So when it comes to simplify that, it becomes SATE squared divided by 4 pi squared. So this part gives the maximum displacement of a building if we model it, if we assume it as a single degree of freedom elastic system. So if it was single degree of freedom system, this was the maximum displacement. Then we say, no, it's not a single degree of freedom system. The coefficient C0 modify the maximum displacement of single degree of freedom system to maximum displacement of the elastic system at top. Then this becomes inelastic deformation at top, and this will increase the deformation if the detailing is deficient. So that's the idea. We start from simple, the best thing that we have to represent the earthquake, which is response spectrum, divided by omega squared, becomes the deformation. Then this has a pure dynamic sense. Is the participation factor if we go through the dynamic analysis. See this. But anyway, so that's the idea. For now, here these two parts transform SA to SD, displacement of the single degree of freedom elastic, linear elastic system. So, but here we call it TE, the equivalent, because we are talking about a building that gets damaged, a building that the stiffness changes. So because of that initial period of the building is better to be modified, because really the building period changes. So an equivalent period should be used. And in each method for pushover, they are using different equivalent period, as we will explain. Therefore, Therefore, we need T of the building, period of the building, we need at two locations, as shown in the footnote. One location is because of changing SA to SD, we need 2, and the omega is dependent on period, so we need it here to change the SA to SD. And second, to find the SA from the response spectrum, we need the period. So period is very important. Estimation of the period is very important. And of course, a building has a initial stiffness, an initial mass, and with the initial mass and initial stiffness, you can get the initial period of the building, the initial building. So if you want an equivalent period, you should define either equivalent mass or somehow equivalent stiffness, or both of them. So then we say, okay, we have initial period because we have the mass and stiffness of the building. This is known. You tell what is your definition of equivalent mass, equivalent stiffness. You define this. Then we divide these two together and reach to this. So, for example, here we say, okay, during earthquake, yes, mass changes. Some floors maybe, some of the mass falls, changes, but it's not that much. But mainly stiffness changes. So, if the initial period of the building is this, and just the stiffness of the building changes, now I give you our estimation of new equivalent stiffness, you give me your estimation of the equivalent period. So if we divide these two, we have this for each building. We have the initial period. Initial period is there. Initial stiffness is there from the pushover curve. I will show. Just decide this. What is your definition of equivalent stiffness? And then you reach to the equivalent period, and then use it here and use it here, and this part is there. So the question is, what is equivalent stiffness? And the equivalent stiffness in each pushover curve, the developer defined it in a specific way. If we look at that, if we push a building here, and this is, for example, target displacement. We don't know where is the target displacement, but we assume that, for example, in my case, I assume this is here. So in capacity spectrum method, which is another way of doing pushover that is implemented in most software, in capacity spectrum. In that methodology, they say, what is equivalent stiffness? They call it secant stiffness. They say draw a line from origin to the target displacement. The slope of this is equivalent stiffness, and use it here. You already have the period of the building, and you already have the tangent to this curve, which is the slope of that here, tangent to this is the slope is the initial stiffness. So this is initial stiffness is known, initial period is known. You are defining, according to your methodology, the equivalent stiffness, get the equivalent period according to that. But in our methodology, in coefficient method that we are talking. This is coefficient. It's not capacity spectrum. It's a coefficient method. This coefficient method say equivalent stiffness is the slope of this line. So we should know what is this line. Is this line there? And in the codes for existing buildings, they explain that you should slope this way from this point, which is the either target displacement or the point that there is a drop in the stiffness. We assume, of course, all things is to calculate the target displacement. We don't know that it's target displacement, but if we assume that it's the target displacement, then later if it was much difference, we repeat the procedure. So from this point, that is our estimation of target displacement. We select this point. Also, we select this point, origin. Then we draw two lines. These two lines should satisfy two requirements. One requirement is the area under these two lines should be the area equal to area of the real building. So the energy between equivalent model and the real model be the same. So the area should be the same. Also, this line at the point that intersect the curve should be 0.6 times this. At the beginning, people were writing codes in Visual Basic or in Excel to derive these curves. Now the softwares themselves derive this curve. So they do a pushover on the building, initial pushover in the building, then they linearize that by this method and find the equivalent. Equivalent is here, then we have the T equivalent. So we have the T equivalent, we have the SA. So these inputs we assume that we have them. This bilinear approximation of the pushover curve, as I mentioned, now is being done directly. Most of the softwares that are being used for the applying pushover. So fortunately, this part not that difficult. So what else we need according to topology, according to the formula? The new value of the CZ, a structural dynamic. If we use the response spectrum, the response spectrum gives us the maximum acceleration for each period, maximum acceleration for each building, each single degree of freedom system. But if the building is not single degree of freedom system, is there relationship between displacement of that multi-degree of freedom system with multi-degree of freedom system between this value that we get from response spectrum? Because people who have studied dynamic of structures, they know that response spectrum is by solving the equation of motion for single degree system. So the curve is for just single degree system. But again, those people at the end of course, when they reach to the modal analysis, they saw that we can use even it is really for single degree of freedom system, but because each mode of a multi-degree of freedom system is a single degree of freedom system, we can use them to just a modification factor is needed, which is the the dynamic factor in the formulation is, has a specific equation, so it's nothing difficult. It's completely based on the properties of the system, the shape of the mode, and this contribution factor is a very well-known factor. But here, because it's a professional code, it doesn't want to be very scientific approach. So usually for these factors, they give tables. They let you to use software, the contribution factors that comes from software, they let you do that, or use this kind of tables. And in this kind of tables, there is a relationship between top displacement of a multi-degree of freedom system and the value that you get approximated from response spectrum analysis, which is for single degree system. And naturally, it depends on the number of stories and on the form of deformation. Oh, so much difficult for me to draw here. Let's try my best. If we have, for example, few stories in the buildings, for example, is base. This is the original original shape of the building. Some buildings, when they under static lateral load, they apply static lateral load. The form of deformation. I can see the parcel, unfortunately. Like this. We call them bending type deformation, like the bending cantilever, for example. And but sometimes some systems they deform under lateral force like this. So we call them, their form of deformation is shear type deformation. So some are shear type deformation, some are bending type deformation. And this naming is not relevant to the naming of the form of deformation in the elements. For example, a shear wall element behaves like this type 1, this type 2, like type 1. A frame with, for example, one bay frame, that's behave multi-story one bay frame behaves like form 1. And when we look at the elements, there is no really bending behavior in elements. But this one bay frame mainly goes through axial deformation in those two columns that it has. One is in tension, one in compression, but generally the building's form is bending. So when we name it as a bending or a shear, we don't talk about the element type of behavior. A frame, you can neglect the shear deformation in beams and columns of that. But the general form of the frame behavior for multi-bay, multi-story frame is like 2. So it's shear type deformation, but you neglect the shear deformation in elements. This is the general type of behavior of building as a whole, not as for their elements. So for the multi-bay, multi-story frame, the elements are undergo flexural deformation, bending deformation, but the buildings show a shear. So what is the relevance to our discussion? You see the bending buildings have top displacement much more compared to the shear type buildings. And also there are many points regarding their structural. If you can see, for example, there are 3 stories here. If you look at the item number 1, item number 1, item number 1, if you look at the first floor, first story, between bottom and top, there is not much deformation in story 1. But in story 2, between bottom and top, the difference is more. In story 3, even more. So any system that has a bending, it will stiff the bottom stories, but it can't stiff the top stories. You can see the drift in top stories is much more. So, for example, a shear wall system can't increase the stiffness in the upper stories because it's a bending type system. A bracing system can't increase the stiffness as top. If you want to increase the stiffness is bottom, but opposite to that, look at the type 2. In type 2, unfortunately, I don't show it cursor, but you look at the first story, bottom, top of first story. The deformation is, difference is too much. The first story, drift is too much. Second story, bottom and top, much less. The third story is almost the same, much less. So if you want to increase the stiffness of the topper stories, you better use the systems with the shear type deformation. And for tall buildings, as you know, as great Bangladeshi engineer Dr. Khan showed, the combination of them is a good combination for the taller buildings. Of course, he's famous for developing other structural systems for cube systems for the tall buildings. Anyway, so if we return to our table, the value of C0, what was the C0? C0 wants to say that from single degree of freedom system to multi-degree of freedom system, you can see, for example, for a 5-story buildings, for 5-story system, for shear buildings, it says is 1.2. So the target displacement will multiply by 1.2, 20% more. But for bending type buildings, bending type 1, which is top displacement is more, is 40%, 1.4%. So in general, in summary, what is the C0? C0 to read the of elastic to elastic deformation of multi-degree of the system. And because it's elastic linear, is pure dynamic of structure type discussion and meaning, and this kind of tables is just to make it easier for professional not to go through the formulation easily from table data. So it shouldn't be a big deal really, the coefficient C1 when we have the this kind of tables. But till now we get a good estimation of the top displacement of the building in the earthquake, in that level of earthquake. So the demand is in our hand. They gave us earthquake, we gave the maximum displacement of the top of the building if the building is elastic. And this coefficient wants to take care of the inelastic to elastic difference. So as we saw, we talked about C1 and C2 in the last session, but I remember at that point there was some problem with my voice and internet, and we lost some of the discussions. So I again explained here. Sorry for some of you that maybe you had the discussion. So the idea is if the building behaves elastic, let me change this. If the building behaves elastic, and if this is the maximum displacement under elastic behavior, if we reduce the strength of the building, what will be the maximum displacement of those reduced strength one? Because we use R factor for the new buildings, and for the older buildings, the strength is not as much as the strength of the earthquake, so they will yield. Is there any relationship between maximum displacement of a system when yields and not yields? Is linear? Is there any relation? It was from long ago that statistically, not for one earthquake, but in average, for many, the maximum displacement is the same. Very interesting, very beautiful, so nice. So if the building is elastic, you get in average this much displacement. You reduce its strength to much less. It damages, it gets this much deformation, plastic deformation. So if you let it return, it comes to here. The large residual displacement. But again, the maximum displacement are the same. We call that equal displacement. And from long ago, the researchers have realized that for buildings with large period, this happens. So flexible buildings, taller buildings, buildings with larger period, they obey the equal displacement rule. But for the short, stiff buildings, unfortunately, the equal displacement rule is not there, and if you reduce the strength, you get increased displacement. You reduce more and increase the displacement increases as you reduce the strength. This happens mainly for the buildings with less, smaller period. There are buildings who are stiff, their period is smaller. And the period that is threshold and is between these 2 points, two behavior, is usually the TS, the period of soil. Is the if the building's period is more than the period of soil that building is built on, they call displacement. If it's less, they call energy. Area under this remains almost constant. So if the strength is at this level, it goes a little bit more because then can cover the same area as the original. But if you reduce the strength too much, it should go much more, that the area under the curve remains as the initial curve. So this coefficient sometimes is 1, sometimes is more than 1. And this formula is take care of that, and the strength is important for the short period buildings. Also, the effect of soil in this alpha, but formula is not important for us. Whenever we want to use, we go and look at the formula and put the numbers and get the result. The concept is important for us. Here remains the last factor. Here is the C2 factor. Again, very if you apply, one discussion was that is it possible to use the same approach for new buildings? The same approach can be applied for new buildings, and some codes, such as Eurocode, Japanese, some codes, Turkish, some codes have the formula you can see. Why? Because, but you can't see C1 and C0. Why is not C2? Because C2 showing the effect of deficiencies, shows the effect of bad detailing. A new building shouldn't be deficient. Any deficient element in new building should destroy and replace. Therefore, new building, we don't need C2 factor. But for the existing buildings, it's very important factor. Shows all the deficiencies, the effect of all deficiencies that is in the detailing that can increase the displacement of the building. Because it is acceptable for us that when an earthquake with a specific amount of energy is applied to the building, and in a specific fuses, in a specific plastic hinges should absorb that energy. If after a couple cycles the behavior of load deformation hysteresis curve of those plastic hinges pinches and the area reduces, the capacity of absorbing decreases. So we can expect that we should need more deformation on horizontal axis to get the same level of energy dissipation as the original very good and fat hysteresis curve. And last time we discussed about some deficiencies that can cause this. Therefore, this factor is very important. Existing buildings, and interestingly enough, it depends on the period. See, it depends on the period too. So buildings that have a smaller smaller period, their C2 is more than the buildings that have larger period. Very interesting. Very interesting. But why a building that has larger period is less compared to a building that has smaller period? But the point is the effect of this side stiffness degradation, strength deterioration, pinch, hysteresis shape. The effect is depend of number of cycles. If this plastic hinge, it goes per one cycle, the difference of good and bad is not as much as if they go, because then the difference will be much more. And if I assume an earthquake is, for example, 10 seconds, the earthquake is 10 seconds. If the period building is 1 second, we expect that we have 10, the length of earthquake divided by 1, 10 cycles. But if the period of the building is 0.100 cycles, so for buildings with less period, they will experience more cycles in the same year. And because their detailing is deficient, in each cycle something happens to them. More degradation in stiffness, more strength deterioration in each cycle. So the effect is more pronounced for the buildings with the small. So for these three factors, evaluation of target displacement. So if we want, again, look at just formula, just concentrate on the formula, the target displacement. The target displacement is estimation of the top displacement of the building during a specific level of the earthquake. We need in the coefficient method a coefficient, a factor to relate the spectral displacement of the equivalent single degree of freedom and building roof displacement, a dynamic parameter. But we also had it in the table form that depend on the building. But I forgot there to say that how we recognize that a building is shear type or bending type. If we have a building, we apply the lateral load to that, and we look at the drifts in the story. If the drift from story 1 to the topper one, the drift increases, is a bending. If it decreases, a shear. So then we can use those tables and find the C0. C1, linear and nonlinear. A modification factor relating expected maximum inelastic displacement to displacement calculated for linear elastic displacement. So in the seismic design, in seismic evaluation, the buildings will experience nonlinear behavior. So the effect of nonlinearity, the effect of damage will be included in the work by C1. And C2 a modification factor to represent the effect of hysteresis shape on the maximum displacement response, which all the deficiency of the existing building compared to the new building will be included in the calculation of the target displacement, mainly C2. SA is the input for the level of the earthquake that we should check. This spectral acceleration at the effective period and damping ratio of the building in the direction under consideration. Then we need to change the acceleration to displacement by dividing to omega 2. And TAE is the effective period of the building in the direction under consideration. And others are just change of unit due to gravity. So we change the unit of SA from G to meter per square centimeter. So it seems we can use this formula. Shouldn't be that difficult. Maybe a couple times it's not that familiar for us, but generally is logical. So now we should have the target displacement. Now we have the software to do the pushover analysis. Now we are ready to calculate the demands. So one part was calculating the demands, and one part was calculating the capacities and comparing these two. For demands, we need to introduce the load combination, what gravity load we should use, along with the pushover analysis as a lateral load analysis, and then we go through the capacity calculation. Therefore, the gravity loads that we should put, because we are dealing with nonlinear analysis, superposition is not applicable. So first we should put the gravity load on the building, and when the gravity loads are there, we should do the push. Otherwise, it's not possible to do separately and sum the results, because this is a nonlinear and superposition is not valid. Superimpose the result. The result with and without, and in the without, then we sum the gravity loads, the results won't be the same. We had it in the previous session, the same for the nonlinear and linear analysis, the gravity load combinations that should be used. I mentioned that previously it was just one formula for the maximum gravity load and for the minimum gravity load, including dead and live. Now snow is added, so becomes 3 combination for the gravity load. So once we should put this on the building and push and look at the results, then separately put this as a gravity load and push and look at the performance and building. And lastly this, and then the worst case for each element is the we use that for the decision making, the performance of the building. Therefore, now everything is ready for the nonlinear analysis of this building. We put the gravity, the target displacement. We calculate that based on the, we'll have different target displacement based on what level of the earthquake and naturally what level of spectral acceleration is given. Then we put the software, we put gravity loads on the elements. We ask the software to use this lateral load distribution, and then software step by step, and we assign what is the step number of steps. Step by step increases the load, doing the analysis, increases the load and doing the analysis till the maximum top displacement reaches to the target displacement. If it doesn't reach, first we make sure that it's not a numerical problem. If there was not numerical problem, say unfortunately the building can't undergo this level of earthquake. But if the building because now when you look at this, you should just see a set of force control and deformation control parameters. Lots of force control, deformation control parameters in the beams column. You just see it. If one of the force control parameters has the is lower bound strength, again we see that building failed. But if it reached to the target displacement, reached, no force control element action, not element. In element we have different actions. No force control action reaches to lower bound strength. So then we can look at the deformation control actions and how much damage they do. If none of them pass the yield, system is elastic. If some of them pass the yield, then we look at the how much damage. And then we know we need the strengths, the capacities. But now is the demand. The demand is done. Now we have the effect of the earthquake on this. So at this stage, now we have the demands. We have the demand. We should decide about the is it acceptable or not. The idea of should be this estimation under that level of earthquake and look at the building and evaluate that. Now we are evaluating. Are they accepted for that performance level or not? For deformation control actions, both nonlinear static and nonlinear dynamic. For what is the acceptance criteria? It says the primary are the ones that carry the lateral load. Secondary, those that just carry acceptance criteria. And for the deformation control ones, the deformation capacity. It's not load capacity. Deformation is plastic deformation capacity. Capacity is not a big deal. If they pass this point, it's not for us that they don't accept it. They are not accepted. No, but we look at their deformation capacity. If the demand is this point, does it have this much capacity? This much deformation capacity? So we push the building. This is the building in general. At this point, target displacement, which is the top displacement of the building. Horizontal axis here is top displacement. Vertical axis is the base shear of the building, whole building. But in the each element, each deformation base, deformation control element, then software, how much is the deformation? And then we check with the deformation capacity. And where we can find the deformation capacity. Wow, that was the main important I mentioned at the beginning, these different codes for the existing buildings, that's their best. So here in the codes for existing buildings, we have two very important. All others are good, but it's not as important as a structural engineer. As this Tuesday, 1st of March at 10 p.m., when you look at this curve, you should enjoy. For a structural engineer, nothing is more enjoyable to see that very easily for existing building or deformation control parameter. Force control, not a big deal. That should remain plastic. But for deformation control element, whatever condition they have, good, bad, beautiful, ugly, whatever situation they have, easily you can find what is their capacities and their modeling parameters, this shape, these modeling parameters, and the acceptance criteria. YO is this much damage, LS is this much damage in primary element, in secondary is this much, CP in primary is this much. So both the acceptance criteria, and the modeling parameters are very beautifully summarized. The results of lots and lots of research and work and experience in simple terms. That's really interesting. Therefore, and previously the only template for nonlinear behavior was this five line curve. So we have force control actions, no need to these curves. Is always they are A to B. And they are deformation. And for all deformation control parameters in steel structures, concrete structures, masonry structure, wood structure, they use the same shape, just the value changes. These residual strength changes, ratios. This ductility before deterioration changes. This ductility after deterioration changes. But the shape was the same. Now for the short shear walls, they have another curve too that with small changes. But other than that, the shape shows the very important. And how we find this modeling, where we can find this modeling and this acceptance criteria, I mean everything that we need. Both us and some of the softwares use these tables in the codes and give us what we need. So this type of tables that for all different systems with different material we have in different sections of the existing. both modeling parameters, A, B, C, modeling parameters, and acceptance criteria. Here, it passes life safety or not? Does it passes the immediate occupancy? Does it passes collapse prevention? So these values are here. Acceptance criteria. Plastic rotation angle. Plastic deformation angle for different performance levels. So these are capacities. Capacity for I/O, capacity for LS, capacity for C. Capacity for linear analysis, because couldn't go through nonlinear, was the M factors. How much the demand is more than capacity. Demand to capacity ratio, how much? 3 times, 2 times for I/O, 1.5 times, how much? So for linear was to say acceptance with for nonlinear the damage, plastic deformation. Plastic deformation, even with the values. Lots of work, lots of experiments summarized. We don't need to go through full scale. Otherwise, it was not possible to apply them in the real life. It just was good for the thesis, for PhD, master thesis, but not in the real assessment of the existing buildings. It was not so simple. A few parameters related, for example, for ductility and for the confinement and for shear, different combinations, and not for good buildings. Most probably the buildings according to code will be, for example, first row or better. But for every deficiency that you have, so powerful. And because of this kind of information, little by little, some of the engineers, some of the researchers saying that there is no need to the ductility requirement in the design codes. There is no need to the chapters on earthquake in design codes. We can leave them aside. No detail, no prescriptive, no empirical approach. We can model. If it's deficient, the value of A is not 0.025. Is, for example, 1/5 of B. So why you make me to use this detailing that you are saying? I do whatever I want, and then check if the building satisfies the performance level. It's okay. We want the performance level, and no building element passes the acceptance criteria. So we do. So there is his history of the fight and challenge between people in favor of prescriptive experience, empirical approach, and the modeling analytical approach now continues, and even becomes more challenges between them. But mainly these are happening by newer generation of researchers. Older generation, they don't trust on all the modeling. These things, they say, still there are some things that we didn't, there are possibilities that many things we haven't seen in the models. It's better to rely on what we have seen experiments in the previous earthquakes, in the prescriptive approaches, empirical approaches. So, but this kind of tables that give you for any efficiency that a beam, a reinforced concrete beam, they have, what is their effect on their modeling, what is their effect on their acceptance criteria, summarize. Very powerful tool that you can model, you just easily go check the details of each building, and for each element separately model. Previously, you should do a full-scale testing to get this. Now, quickly. And this. So really, you should enjoy. All of us should enjoy. Pray for the researchers that have done this great works over the years, and those people who summarize them. Very nice work. Therefore, here for any of the systems that we may deal, we have this kind of information, and the checking of modeling and checking of the deformation parameters can be done. So, how about the force control parameters? That was for the deformation control parameters, those tables. For force control, just force. It's not important. We don't need table, and just put the load combination on the element, push the element and this building, and then check the forces and the capacity, lower bound capacity, lower bound capacity of that capacity will not let. Previously, the demand was simple. Now, make it more accurate. They say that from the results that you get from the putting both earthquake and gravity, and then you get the shear, for example, in this element. Remove the part that if you just have the gravity load, then this part we need to put some modification factor, that this modification factor shouldn't be applied to gravity load. So we should reduce the gravity load, put that modification factor on that part, and then add the gravity load again to this one. So this part, before we didn't have that. It was just this with this, and it was controlling with the capacity, the demand. But now they put two factors. One factor is because it was a little conservative, the way that we did for the controlling the force control options. Now divided to three items, that if it's really critical, it's more conservative approach is not that critical, less, and one factor for the consideration of the performance level, because during the lots of study that is being done, it is shown that if you the building, for example, the force control elements for life safety or immediate occupancy, you need more conservative approach toward the force control elements. But if you look at them at the collapse prevention, you don't need. So for life safety and immediate occupancy, they increase the level of the demand in the force control element, but for collapse prevention, they do. And also another factor that to apply to critical elements. Critical elements are the elements, the force control actions that if they fail, few bays or few story of building will collapse. For example, there is a column in first story. If this and the building is 3-4 story, and if this fails, this column fails, a few story. If no story or bay collapse, just element collapse is not. So there was some modification, but it's not a big deal because you check the force at the capacity, the strength of the element. Here, whatever accuracy we want is easy. How many factors they want, we will put, because these are forces. It's not that like a deformation control, you want to check the plastic deformation, the table, these things. So for the force control elements, check the demand with capacity of lower, the same as linear. Therefore, the general approach will be we model the building. We model the building in a software that can perform nonlinear analysis. Then we go through or use the software or manually calculate the target displacement. So target displacement will be calculated. Then we ask the software to apply the lateral load distribution, the pattern. For example, 1, 1, 1, 1, 1, 1, if the uniform load pattern should be applied, whatever our code, specific code or methodology was. Then the software will apply the loads and look at the formation control elements and force control elements. If force control elements reaches the extent is gone from our point of view, for the deformation control elements actions, usually software with call or check so that, for example, if it reached to point B, the specific shape, point reach to IO with another shape, with LS other shape, it reaches to CP, C, D, or plastic in shear that reaches to the collapse at this point. So the efficiency of the building is seen clearly, and the severity of the damages at that level of the ground motion can be seen and investigated. And if we want, then we apply some retrofitting techniques and redo this to see if it reaches to the level that we want or not. We discuss about the nonlinear which the building costs, they are still relying on non-linear static, which is strange. Static, the earth is cyclic, is not static, is not push over, but still uh, only at points that the efficiency of non static is such as design of the tall buildings, and tall buildings, the effect of the higher modes is very much, and you can't neglect them. Still, for a long time, codes are relying on the static. The point is, and when there are lots of research that if you go and check the results of nonlinear dynamic analysis, that is a simulation of earthquake, with the results of nonlinear static analysis, the results are not quite the same, and you always use the nonlinear dynamic analysis as a judge. But the point is, this judgment is not really uh, the point is, if we have the input, the best approach is nonlinear. If you have the input, if a person can confidently say that, check my building here, and this is the record that will happen. The best is nonlinear. But unfortunately, even on one fault with the same situation, never two records similar happen. And the non-linear usually is very sensitive to the records. It's very sensitive to it. So even if you select one, though when you apply record 2, this is the building is gone. 3 is 4 is L, 5 is something. So sensitivity to input. Therefore, nonlinear dynamic analysis is mainly used when you have the record. For example, the earthquake happens somewhere, you have the records, you have the building characteristics, you go and model the building and apply the record and check that if the observed damage with the calculated damage are similar or not, and you get lots of good points about the modeling, that, for example, why the reason are not the same. If I change the modeling of this infill this way, the results become the similar, and lots of good points will be resulted. But where we have the record. So now that we are going little by little toward the nonlinear dynamics, now, first of all, the codes try to ask for too many. So, also, they are, because say the mean of the results should be okay. Yes, it's very sensitive to the records, but we went the too many records, too many suitable records. If you use these results, most probably getting better. Therefore, first they want more records. Also, they are working on the way that selection and scaling of records improves. So with the smaller set of records, we get the same mean results as a bigger set of records. So that's why we It's a comparison of results of nonlinear static analysis with nonlinear dynamic analysis is not useful because the results of nonlinear dynamic analysis itself is not reality. There is no reality there because you don't have there. And which any difference in the characteristic of the earthquake at the same level, the result changes. But at least in the static analysis, nonlinear static analysis, there are a couple points that they can put a specific level of conservatism there, such as calculation of performance level, load distribution that is being used, and so on. So if we summary our work, because anyhow there is an exam coming up, there is, what is the pushover analysis? There is pushover analysis. Pushover analysis is a kind of nonlinear static pushover. What is the target displacement? Target displacement is to model the earthquake, the maximum displacement that the earthquake, the estimation of the maximum displacement of the building in earthquake is the what is the load, this lateral load distribution that is being used to push the building? That's the for deformation control actions. For deformation control actions, what is acceptance criteria for deformation control action? Is deformation. It's not force. Deformation capacity shouldn't be less than deformation capacity, either bigger or equal, shouldn't be less than this. So the capacity, for example, deformation capacity, if you are if we checking for the life safety, the capacity is here, demand is here, demand passes, so it's not, life safety is not accepted, it's not attained here. Therefore, the deformation capacity for that performance level should be not less than the deformation. However, for force control action, look at the forces, the strength, the lower bound strength, the strength that in calculation, the lower bound characteristic of material is used should be not less than the demand. Now we look at the pushover today, linear static analysis previously. What are the main differences? What is the main differences in pushover? The effect of damages are considered. So wherever the stiffness matrix should changes, distribution changes, we don't need to manually adjust the load combinations to get the effect of distribution. So what are the inputs in pushover analysis? So we have these four. We have these four: target displacement, control point, load pattern, and the most important is the modeling part. Again, such a like the linear analysis. If a nonlinear analysis, a force control action does not satisfy the acceptance criteria, what is the building performance level? Fail, collapse. So no performance level. And in linear analysis, the load combination linear analysis, the subject of previous session. In linear analysis, the load combination for load control and deformation control are different. Why in nonlinear analysis they are the same? We don't use different load combination as in the linear analysis we divided by C1, C2, J for the force control actions. Why we don't do these things? Because the effect of damages are included, are considered in the nonlinear analysis, but because it's not considered in the linear analysis, we had to do those kind of adjustment ourselves by changing the load combination. Why nonlinear dynamic analysis has not been the preferred approach of analysis yet, but will be because of we don't have an answer to this question. What will be the characteristics of next earthquake? So we apply that. So there is a big problem to how to select the earthquake records and how to. Therefore, in general, have a view of the advantages, shortcomings of nonlinear analysis. We got some familiarity with calculation of target displacement for the buildings. So when we look at a building and we want to evaluate that, we see force control actions, deformation. And now we differentiate between them. And now we know who are friends, who are enemies. Determine the load combinations. Now, force control and deformation control is almost the same. And in general, we know how to apply procedure. With this, I think we can go directly thanking you, Salam, and go to the question and answer.
Thank you, Dr. Mogadon, for a nice presentation.
Thank you very much.
Today we have, I say, very few questions actually. There are actually 2 to 3 questions on my side. 2 of them are, one is saying to please refer some software and handbooks.
Okay, so questions are yeah, regarding software, I can see. So I can see lots of, okay, yes. Please refer some software and handbooks. I hope on last session, which is on Saturday, I will go through the areas, just saying that our course focuses on this area regarding the existing buildings, and these other areas are not covered. I identify some of those. Also, at the same time, I will include some of the references both for the evaluation and modeling and analysis, also for the retrofitting. So I will do that the next one.
Thank you, another one was saying that to show some practice example or to provide some practice example, that would be helpful.
Okay, so the same I will also introduce a couple. One of them is almost new, goes through the different chapters of these codes and provide samples of the building application to the buildings. So I will provide that one too.
Thank you, Mr.
One of the I think our dear colleagues also ask for annotation. Right now comes. Sometimes I saw a message like this comes and goes, but this one is a state. So I think I can approve to see it's just our colleague is checking or wants to write something. So I approve because this one is a state. Usually they come and go quickly. I I gave the annotation permit, I think, to our dear colleague. If has something to do, we are ready.
Dr. Magdum, you may check your question and answer section. If there are particular questions to you only, then
How can find? Okay, my question. Good. Oh, and most of them is related to the sorry. Seems the quality of voice bothered many of our colleagues. No, is not really any specific ones there too. But if right now uh, somebody wants to even talk, I don't know if that possibility is there or not.
how would you allow only to ask in the questions and answer session? That would be helpful for us.
Okay. So to document that, reminder. Okay. So
Yes.
I try to be on time because
Sorry,
if I did know, I would give more landmarks, but okay, some dear colleague asking that nonlinear analysis only applicable. What is the basic characteristic between linear and nonlinear analysis? Very fundamental questions. As our dear colleagues the day before also mentioned, the nonlinear analysis are also little by little are included in the codes for the new buildings. Do we expect any change when it is new building and existing buildings? Yes, because there are some difference between new building and existing buildings. For example, for existing buildings, we have a better estimation of loads. So we don't need that much load factors or load combination as we need for a new building, that there are possibility of the change in the loads and the these combinations. Also, for new buildings, usually we have, that was true for the load combination. In other aspects, usually for the new buildings, we have more level of conservatism. Therefore, if, for example, we look at the here, for example, these values that we have for the new buildings, and for the existing buildings, they can be somehow different. Usually, for the buildings, they use a little bit more conservative approach to apply them, because for the new existing building, we have more information about the dimension of the elements, about the material, the arrangement of reinforcement. But for the building that wants to be designed right now, maybe during construction, there will be some changes. But in the new existing building, everything is in front of us. So if we can collect the information perfectly, there is no need to the overestimation by adding conservatism to modeling. So some of the acceptance criteria, some of the modeling criteria for the new buildings and existing buildings can be different, but the general body of the approach, for example, target displacement needed. We saw that in the formulation for target displacement for new building, we don't need a coefficient that take care of the effect of deficiencies in the modeling. But some modifications is needed, but the tools that are provided can be completely used in the new buildings. The same software that is prepared now for doing nonlinear is used to, it can be used for the new. Just is the matter of the code developers and the authorities, the code authorities, to let using it and in what area they let it. For example, if you use the approach for existing buildings, you can omit the need to R factor. But in some people, some codes that they are using non-analysis, they say that they just let the nonlinear analysis to be used for the optimization of design. In a way, they say that you should at the end check with the linear methods. Still, they are not completely comfortable with the nonlinear analysis. Not that the method is conceptually weaker than the linear. It's conceptually is stronger, but we are not that familiar as an engineer with the methodology. Our softwares and then if there is error, it is very difficult to find sometimes the errors. But in the linear analysis, very quickly we'll find the errors. Because of these concerns, many of the codes, they said they have chapters or appendixes on using nonlinear analysis for design. But at the end, they said, then you finalize your design, you go and check with the linear analysis. Some of them, they give you some values like 20%, 15%, 10%, that if you pass the limit for the drift or limit of the stress ratio, if you are doing nonlinear analysis, it's okay. But anyhow, they ask to do the, if you got the results, and the results were approved by nonlinear analysis. But when you come and check with linear, it is 20% more drift or 20% more most linear methods completely. So then the question will be, what is the use of then if I have to satisfy the linear method, what I want in the new buildings? But because there are many infinite configurations for a building to satisfy the performance level, the good point about the non that and you know end up with lots of relation reinforcement. This thing that you can result and approved by elastic analysis, but nonlinear analysis will help you to find the optimum one of those, and then introduce that to the elastic. Therefore, there are possibilities, and I'm sure that for the new codes, they will go toward the nonlinear methods little by little as the software, the familiarity with the software increases, results that you can get on performance, on consequences, much more information you can get from this kind of studies. Also check there are some questions, I don't know. How can they develop backbone curve based on concrete section and arrangement of reinforcement? They usually, if you use some of the commercial softwares, these commercial softwares should click that. Yes. How can in some of the softwares they have modules to do section analysis, but in general, the good point about these tables that I don't know, I think you can see the table right now. The good point about the table is that it's provided for you those information for sections that you want. You want the concrete section, beam, column, arrangement of reinforcement. So based on the arrangement of reinforcement in column 1, rho minus rho prime divided by rho balance, based on the arrangement of reinforcement, you see that which row you are in, and based on the transverse reinforcement in the second column, and based on the value of the shear third, so then you have your curve. Those A, B, C are the value of curve. But if you don't want to use this curve that is already and is an important aspect of this, if you don't want to use that, they let you to develop your curve. But these curves, the good point about these curves is they are derived from the experiment results that are based on cyclic analysis. So the effect of, you can see from point A to B and B to C, and then the drop of the stiffness. So those effect of, such as strength deterioration, stiffness deterioration, these things, those cyclic effects are seen in these curves. But if you use any section analyzer, usually gives you the under monotonic loading. Of course, some of them also have you can introduce the material properties based on because you should, as an input, give the stress strain curve to them for the material, and then give the distribution of concrete and reinforcement in the section. With having these two, the software do the section analysis and provide first the, for example, moment curvature curve, and from the moment curvature develops moment rotation curve. Section designer, section builders, you have seen in the commercial softwares, they do this. So if there is in a building, an existing building, in a new building, you find a section, a strange section, for example. One part is steel part, one part concrete, one part is, for example, another kind of alloy. If you go to the section designer, give the geometry of the section and the different part material. This part is steel, this part is concrete. This part is, for example, alloy. Then the program go find the neutral axis based on the mission that you provided. Then it starts to apply a small curvature to the section based on the curvatures and each of these material, the distance of each of these material to the neural line finds the material, then from stress strain curve, the stress, and then by the area of the that section, stress to force, and then by multiply force to the distance to the x, the moment. So from it covers from the horizontal axis, builds the value on the vertical axis. Horizontal axis is the curvature, vertical axis is the moment. And the curve will develop that. And when something damage happens, it's not working, it changes the location of neutral axis. They prepared. Also, there are now very many softwares that do the fiber analysis. It's the same thing. So there are many options. The codes for existing building let you use of them to decide is better because has the effect of cyclic iteration. But otherwise, this question is can be done. There's no problem. Our dear colleague asked about the nonlinear modeling of shear wall, which is very good point. Both for the new and for the existing buildings, there are many aspects to it. Both is very difficult to discuss, but in general for taller shear walls, because usually a taller shear walls behave the and undergo plastic deformation in the flexural hinges, and the shorter beams will go nonlinear behavior in shear mode, because when it becomes shorter, they become very stiff and flexure, so the shear deformation increases. Therefore, the general characteristics are quite different. For taller ones, the boundary elements are very important. Most of the ductility comes from the boundary element, but at the same time, they are very sensitive to the amount of compression in the compression part of shear wall. And many of them damages in the like Chile earthquakes, like Turkey earthquakes, places that they have concrete shear walls, the long shear walls, tall shear walls, was due to this phenomenon, and because of that, they generally they limit the amount of axial force due to the earthquake. For example, 0.35. But for the smaller ones, there are a couple mode of failure, and mainly in shear. And for them, both the vertical and horizontal reinforcements to get the shear are very important. Now that you mentioned that, I should write somewhere to. There are a couple very good references. Says shear wall. I will try in the presentation on Saturday. I'll add the samples. So if you are interested, you give you a step-by-step very good view, and specifically on shear. Then in nonlinear static procedure can be applicable if we wish to design a new building as per NBC. Please be informed that study process is included in our new code as analyst tool section. Very good. So if it is included, I should check this part. Because what the acceptance criteria. Because the building codes doesn't have this information about the area. In fact, the table that is most probably you can see in the screen. These tables, they don't have the tables like this. So there are two approaches for the new building that now I can check for the NBCC see that to check that if it is included or not. But other codes follow one of these. So they don't have this information. What is this information? It says that life safety is, for example, when the plastic rotation is this much for this case. So give you some numbers. But because they don't provide this acceptance criteria, they go like this. They say, you do the nonlinear push-up. You accept for new building, you do that. But you should calculate the target displacement. You push the building the target displacement. Then some of them ask that you continue 1.5 times target displacement, and there shouldn't be any deterioration in the base shear top displacement curve in this range. So they don't need those kind of acceptance criteria that are not provided. They say that you just push, check that if you go 1.5 times target displacement, still building is stable, and at the target displacement, if, as I mentioned, if the drifts and the stress ratios are less than 1.2, it is over. But the other type of new building code that apply nonlinear static or nonlinear dynamic, they say that model, do pushover, do nonlinear dynamic. Then when you want to check the acceptance criteria, refer to the codes for the existing buildings. So this way, they solve. Okay. So thank you very much. Corrected the section 2, 5, 12. For sure, I will take that. Thank you very much. Table 10, 7, the table that is on the screen. Which loads or load combination should be used to calculate this V that is here? What load or load combination is better to use here? The best option is that for each load combination, to change the properties of the hinges based on the view for that load, which is a little difficult. For each load combination, you change the properties of hinges is too much. So people usually use the worst case. On the load combination, the V that is the maximum one, they use usually V conservative. But the advice is if you do that and then saw the results is sensitive to this, then use this first approach, changes. So most probably get the results. For each load combination, use the V of that. Please give us information about the beam column joint modeling in nonlinear static procedures. And not in general, there are the approach in these existing building codes is they give you a minimum requirements and the tools, but for much more advanced modeling. For example, in the chapter on reinforced concrete, it mentions that you can model the beam column as rigid. So there is no need to model. But just the table to control it, to see that the joint is in damage or not, the control, but not model it. So that's the minimum requirement. But also give you the way to model both for reinforced concrete and for steel structures. The same for soil. It says that you can accept IO when we check for IO. You can use the fixed space modeling for the building. But there is a chapter completely on modeling the soil with springs, which is very, very nice. And many times if you use those modeling, the same that you mentioned, beam column, or soil, the performance of building improves. Because when the connection rigid, or when the connection to soil is very rigid, usually damage concentrate. But if there is some flexibility, the damage will distribute among load and damage distributes, and the possibility of getting the performance approved is much more. So the codes usually set the minimum that is acceptable, but you have this opportunity to discuss with the in a real world, because one talk is research and one talk is about the real world. So the owner knows that if you go with the minimum, you satisfy the requirement, and if you are doing more, you should be considered for because but this extra, especially for the existing building, can be quite beneficial. If these are lots of retrofitting, the big difference in reality. But the money that they give, for example, for extra work to an engineer is not comparable to that problem of disturbing the situation of the building, doing the retrofitting and these things. Therefore, we have the tools, but some of they are not obligatory. Is it possible to present a real life example from the one much? Yes, that's a book mainly of the school buildings in Iran, and different methodology that is being used for the retrofitting of the general approach, the same as using, but on two example, I have generally go through to show a couple points. I already included for the session on most probably it would be difficult to add anything new to one session, but I will look at that. Thank you very much for looking at those references. So if you are using this on modal analysis, yeah, and its mass participation mass ratio as per can be performed. If not, how can we solve the problem to perform nonlinear? There is 2 points. One point is methods for doing nonlinear pushover for different cases that ordinary nonlinear pushover analysis is not applicable. We have lots of solutions in the literature, from very well established solution to include the higher mode effects, classic work of the Chopra and Goel for modal pushover, to the consecutive pushover that is seems that is the best or one of the best for the taller buildings, and exactly around the same mass ratio that you mentioned is used as a threshold. So there are methodologies that you can apply to extend pushover analysis to the cases that ordinary pushover is not applicable. But the point is, for research, we can do. But for real life, usually the peer reviewer, the controllers, they just ask for the, usually, they ask for the code that you apply the code provisions, not the research type of methodologies. Sometimes they agree. You provide the background, you provide the validation, and they agree to use that. But otherwise, if such cases that you mentioned and your mass ratio is not satisfying, and then you have to go, for example, doing the dynamic analysis. Usually they made you to do that. As far as my experience shows, usually it's better to do that, especially now that the problems with the nonlinear dynamic from before this, we were telling that there is no good software to do nonlinear time history. Nonlinear time history is very time consuming. The outputs are very much. But now the numerical problems is too much. But now most of the problems solved, and with these new approaches to select and normalize the records, the possibility of using that is there. So if they accept that you don't use the techniques that is in code and go beyond that, you have much more. Otherwise, you have to switch to dynamic. Soil structure intelligence based on SC41. This suggestion on the topics, I think you should direct to Mr. Rudra Salam and to Dr. Bush and our colleagues that arranging the topics for code. I'm sure they will consider all the ideas for this type of seminars. But I assume that is a good topic, both for new code, the soil structure interaction are very important, and for the existing. For both are very important. Thank you for suggestion. Assume we can conclude.
Yes, thank you, Dr. Mogadam, for your presentation. And thanks to all participants for attending. The quiz and the recording of today's session will be available on our PRP portal. Hoping to see you all soon in our next session. Thank you.
Thank you. Thank you very much, dears. Have a good night. Goodbye.